This is Tessa, Claire, and Brandon's video project. We will be demonstrating rotational dynamics in a few aspects of gymnastics.
Here we have a giant on the high bar into a double back tuck flyaway. Because of the ice skater theory, when the gymnast tucks into a ball, the distribution of weight is moved toward the center of mass, thus giving it a positive angular acceleration. During the rotation around the bar, the angular velocity is calculated to be 3.65 radians per second. During the first backflip, the angular velocity is calculated to be 8.85 radians per second, giving an angular acceleration of 1.56 radians per second squared. During the second backflip, the gymnast's angular velocity is calculated to be 26.18 radians per second, giving an angular acceleration of 15.07 radians per second squared between the two flips. These calculations show that angular velocity is greatly increased by moving weight toward the center of mass. The total angular acceleration in this example is 6.02 radians per second squared.
In the second example, we have a gymnast performing giants around the bar into a layout flyaway where he stays in the same body position he was in for the giants. Because there is no change in the distribution of weight, there should be little to no change in the angular acceleration. During the rotation around the bar, the angular velocity of the gymnast is calculated to be 2.76 radians per second. As the gymnast goes into the layout flyaway, the angular velocity increases by 1.66 radians per second, giving a new angular velocity of 4.42 radians per second. The angular acceleration that happens as the gymnast goes into the flyaway is 0.25 radians per second squared. Part of this acceleration can be explained by the loss of the frictional force between the gymnastic's hands and the bar when the bar was released. This shows that by keeping the distribution of the weight the same, the angular velocity will stay approximately the same throughout the skills.
In the video, a few topics were mentioned but not explained. Here we will go into more depth on these points. First, we will describe the ice skater theory. In the instance of someone spinning with little to no friction, as they bring the mass towards their rotational axis, their angular velocity will increase. This is proven by showing that the constant of angular momentum is equal to moment of inertia times angular velocity. If the radius of the mass is decreased, moment of inertia will decrease as well, causing the angular velocity to increase in order for the equation to stay balanced. Next, we will explain the process of finding the values we used in the first example. During the giant, we found the time by using the difference of time on the recording for each skill. During this process, we also found the amount of rotations made within that time. The equation for finding angular velocity is angular velocity equals the angle of rotation over the change in time. Once we had all of the data and the equation, we plugged in to find each skill's angular velocity. Once we had the angular velocity of each skill, we could plug our data into the equation of angular acceleration equals change in angular velocity over change in time, thus giving us the resultant angular acceleration. For the second example, we used basically the same process for finding the angular velocity and angular acceleration of each skill as the first example. Thank you for watching this explanation of how rotational dynamics work throughout a few of the gymnastics skills.